I will see everybody again next Tuesday.
No class Thursday?
No class this Thursday.
Every bar?
Yeah, this class. So I'm going to Yankees game. Won't be here.
I couldn't let you show me up with the last time, so.
Yeah.
So hold on. There's yours. All right, so we did parametric and polar. Now we get to move on to chapter 12. I'm going to quickly go over three-dimensional space. You're not going to see a question on the test for three-dimensional space. The only reason I'm going over it is because we're going to do vectors, and some of the vectors will be in 3 dimensions. So I just want to make sure that you understand what the space looks like, basically. You probably have seen some kind of three-dimensional space at some point before, but I just want to go quickly through it so everybody understands what it looks like and things like that first. So three-dimensional space, you have X, Y, and Z when you do your points. Your X typically, like if you're going to look at it on a piece of paper, your X comes out of the paper, so that's your X. Your Y is kind of like your X on, if you were looking at it flat, that typically would have been your X. And your Z goes up. So that's your X, Y, and Z.
And that's just standard.
Yes.
They'll never swap it on you.
Mm-mm. The only time you'll ever see it swapped was if you're doing modeling in 3 dimensions, because you can turn it so like the planes might change, but that is the standard convention when you're graphing or trying to draw it. So when you're looking at planes on this, so like if you're going to draw a line, say y equals x, in 3-dimensional space, because there's a z, it actually would be a plane. Because it's going to be a line, but that line is going to exist all the way through the z. So if you only have an equation that's on one of them or 2 of them, you're going to have it expanded into 3-dimensional space. So, for example, if you look at, if we had x squared plus y squared equals 1, that's a circle. If we just had that, it would be a cylinder because the z is everything. So that circle basically exists at every z point. If I said z is 3, then you'd have a circle at z is 3. So those are 2 representations depending on what you have. You also can isolate it down too. It doesn't necessarily have to be the whole thing. If you were going to draw a sphere, it would be x squared plus y squared plus z squared equals 1. That would give you a sphere centered at 0. We're going to look at a little bit more of that in a second. But that's basically all there is with 3-dimensional space. One thing that you do use quite often is the distance formula. So if you look here, the distance formula typically is you subtract the x's, square it, subtract the y, square it, and take the square root of it. It's in essence the Pythagorean theorem. When we expand that to 3-dimensional space, it's the exact same thing, except you also have to add the z in. So if we were going to look at the distance between these 2 points, we have the square root of, we subtract the x's, so 2 minus 1 is 1 squared. Negative 1 minus negative 3 is, no, negative 1 plus 3 would be 2. Those 2 negatives make a positive. Negative 1 minus negative 3. And then 7 minus 5 is 2. Add them up, so you get 4, 8, 9, so square root of 9. So this distance is 3. So it's no different than the actual distance formula that you've been past. It just adds that one other dimension. All right, we're not going to do the sphere. Just because I don't think we really need it. Any questions with three-dimensional space? Because otherwise I'm done with it. Have you guys all seen three-dimensional space before at some point?
Like the graph, really.
Yeah, graphed or using it, or it's one of those things like everything we do is in 3 dimensions. So it's like it's actually used quite often, especially in modeling and stuff like that.
Yes, I've seen videos.
Yeah.
I have.
One of the number one questions that seems to show up on the SATs and stuff like that is they'll give you a cube and ask you for the distance between the 2 diagonal points on the outside of the cube. That's in essence the distance formula, if you know what you're doing. So, because you just look at it in 3 dimensions and say, okay, here's my graph by 2 points, find the distance formula between it. If you don't, then you have to figure out, okay, now I've got the Pythagorean theorem of this one, I find the distance formula of that line, and use that. It's a mess. But if you know the distance formula for 3 dimensions, it makes it really, really simple to do. But it's one of those things that we use it quite often. You don't typically see it done in math that quite often, purely because it's a pain in the butt to draw that in a book. It's really hard to draw 3 dimensions in a book. It's really hard to show 3 dimensions on a flat screen because it's flat. So it makes it a little more complicated, so people tend to not do it. Yeah.
You have math books that are like pop-up books.
If I was still teaching high school math, I would at this point I would have 3D printed all the different shapes and everything else, so I could just say, here. All right, we're done with, in essence, 3-dimensional space. We're going to do vectors. Has anybody here never seen vectors before? Everybody in here has seen vectors at some point? If you've taken physics, you've seen vectors. All right. So, a vector. These 2 vectors actually on the screen are exactly the same. Okay, they're the same length, they go the same direction. It doesn't matter if they're shifted. Okay, so these 2 vectors are actually equal to each other. When we're writing a vector, you can write it a few different ways. You can write your vector as AB, or you can write your vector as V. Okay. The symbol above it, you probably saw when you did geometry class, was a radius, or not radius, a ray. That circle stuck in my head. Very similar in essence to a vector, because a vector has a start point and then has an end point. So you kind of have, well, it depends. Vectors can have an endpoint or they can go on forever, depending on the direction you're going. Either way, though, you have your points. So, and we list it as array, not as a line segment. Hold on, I closed the screen. Trying to get back in. So these 2 vectors, vector AB, is equal to vector CD. Because they are going the exact same direction, they have the exact same length. Even though they don't start at the same point, that doesn't actually matter. Adding vectors. When we're adding vectors, you are going to basically add the components of it. But it actually does not matter the direction you go, because addition is commutative. It goes either direction. So we could add the vectors, and no matter which way we want to add the vectors. You can do u plus v or v plus u. Also notice that it doesn't matter where we're starting it. So I take my v and I'm putting my u at the end of v and going in that direction. The direction matters and the length of it matters more than where it is located in space. Right? This allows us to move things around to find the sum of the vectors. We're going to look at a few different types of multiplication of vectors. Next week, we're going to look at the dot product and the cross product. Those are two different ways of multiplying vectors. Today, we're only looking at scalar multiplication. Scalar multiplication is just a length. So my initial vector was v. If I have 2v, it's twice as long. Half v, it's half as long. The negatives tend to go in the opposite direction. Okay? So it's literally 180 degrees split. And then if I'm multiplying by negative 1.5, it goes in the opposite direction and is 1.5 times as long. If my scalar is 0, it's my vector is 0. It would cancel it all out. Put that in there. Hold on a second. I did not. So when we're looking at scalar addition or addition of vectors, and we look at scalar multiplication, how do you think subtraction is going to work?
Adding it, but you're just
Yeah, you're going to basically you switch the direction and then add. So that's in essence how we're going to do subtraction. So we have our u and v. So u minus v, so you have the u, and then we're doing the negative v, so that's the minus v. Goes down. The only thing different they did in C, they just started at the end of V and went backwards to the U. Yes. Oh, okay. So that's how you do scalar or vector subtraction. All right, now on to actually all the work. All that was just basically explanations. Now let's actually do some problems. Okay. You're going to see two different ways to identify a vector. The first one is based on the components of the vector. Now, remember what I said. It doesn't matter where it starts. The vector tells you is the two pieces that you need to know about a vector is its length and its direction. So if we just assume every vector starts at 0, all I need to know is the endpoint, where it ends. If I know where it ends, that tells me my vector. Because from that, I can figure out my length and I can figure out my direction. So the component is written like this. So it's not a parenthesis. It's actually a almost like the greater than or less than symbols. So it's that triangular type bracket. and that's going to be your endpoints. If it's in two-dimensional space, I have 2 points. I have basically my X and my Y. If it's in three-dimensional space, we have my X, Y, and Z. So it's no different, just got 3 components to it. So if we look at all these points right here, or all these vectors right here, they are all the exact same vector. They are all region. Because if we look at, so if we start to look at these are all going to be 3, 2. Let's take this one right here. If I did 4 minus 1 and 5 minus 3, what do I get? 3, 2. So to take the vector at the points and represent it in component form, I would just subtract the 2 points, the starting point and the ending point. And that, in essence, takes it and shifts it down to starting at 0, which gives me my component. So for the problem that they've given me here, they gave me 2 points. 2, -3, 4. Okay. And B is -2, 1, 1. So what is this vector? Not 0. So we have, so it's starting at A and going to B. So it's -2 minus 2. So it's -4. We have 1 minus -3. So that's 4. And then we have 1 minus 4, which give me 3. Direction matters. So A, it started at A, and my terminal was there. And we're subtracting it. We subtract the terminal from its terminal minus initial. Okay? Because if you did it the other direction, my direction would be wrong. Because if we did -2 or 2 minus -2, I would have gotten 4. All the signs would have been backwards. Okay? So that makes a big difference when you're looking at your vectors, making sure you know where you're starting and where you're ending. All right, so we've got 2 vectors here. And we're going to find some things about them. I'll write them a little bigger. All right, the first thing we're going to look for, and no, that's not the absolute value of A. This is the distance. Or magnitude. The reason I wrote distance is because that's the formula we're going to use, which is also known as your magnitude. Okay. So the magnitude is your distance formula. The difference is that, remember, a vector always starts at 0. So I only have the 1 point. All my other points are 0. So I don't need to actually do a subtraction because I've got the point. I've got my distance between each of the points there. So my magnitude for this is just the square root of those three values. So 4 squared plus 0 squared plus 3 squared. So my magnitude in this case is 5. I'm not looking for the magnitude of A to B. I'm just looking for A. That's why I'm not subtracting anything in this situation. The vector, by definition, does the subtraction already for me. Does that make sense? Good. Now find me the magnitude of B. So I've got negative 2 squared plus 1 squared plus 5 squared. So yes, the square root of 30. Okay. So magnitude's pretty easy. It's also one of those things that's used quite often. So you're going to see that somewhere. We're going to use that a lot, even when we're doing the stuff next week. You're snoring. All right. Next thing, let's do some addition and subtract. Let's do some adding and subtracting and some scalars. So let's do A plus B. So when you write it, you're going to write it as a new vector. So adding is just adding. So 4 plus negative 2 is 2. 0 plus 1 is, and 3 plus 5 is 8. That's my new vector. Now, if you're doing subtraction, you can just do the subtraction. Or you can multiply it by a -1 and do addition. It doesn't make a difference. In this case, let's just do the subtraction because I don't have any other numbers that's going with it. So 4 minus a -2, 6. 0 minus 1, -1. And 3 minus 5, -2. Make sure you do the correct order. Subtraction matters. Okay, so otherwise your direction is going to be wrong. All right, 3b. So this is a scalar multiple. So we're just going to multiply all the numbers by 3. So -2 times 3, 3 times 1, and 5 times 3. And that's my new vector. All right, your turn. Do 2a plus 5b. So it should be -2, 5, 31. This one, you got to do your scalar multiples first. Order of operations still applies to this. Multiplication before addition. So we multiply by 2, multiply by 5, and then we add them together. Yes. Yep. No, so these aren't points. These are still vectors. So there is no terminal in it. In essence, those are your terminals because the initial points are 0. So you're just using those points as is. So once it's in that form, so if you have a vector and it's with parentheses around it, it's giving you the terminal initial, you've got to change it into the standard vector. All right. If it's in this form with those triangular parentheses around it or triangular brackets, then it's in vector form, and you assume that that's your terminal point going from 0, 0. Okay? You are going to see this done another way. Let me do that one. So because we can write vectors as additions things, we have 3 special vectors. We have I, J, and K. They correspond to your X, your Y, and your Z. So I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. If I wanted to take a vector and there. So here's a vector, A1, A2. Okay, that's my terminal point. So if that's 1, my I is typically 1, I can multiply for whatever that number is there times that vector and F, right? That would be just basically your first component of your vector. Same with the J. I can take and multiply by the Y point, the Y coordinate, as my scale multiple. So, for example, let's do a nice little example here. Let's say my terminal point is 5, -2. I can take that and say 5 times 1, 0, 0 plus -2 times 0, 1, 0. So yeah, and the nice thing is since we know it, we don't have to write it out. So actually, this is only 2 points, so I only really need the 2 numbers on this one. So in this case, we'd have 5, 0 and 0, -2. So if we add them together, that would be my 5, -2 as my vector. Okay, does that make sense? No. Yes, because I started off, I'm assuming my point is starting at 0. So if my terminal point, if I'm starting with my initial point 0, it doesn't change it. So that point gives me that as a vector because I'm starting at 0. Okay. The reason I'm doing this is actually, it's another way we can write the problem. We don't have to necessarily write it in that format of that. Another way that we can write this is my vector equals 5i minus 2j. That's another way to write this vector because the I and the j are constants that we know. Okay? Does that make sense?
No, yeah, I get it.
Okay. Well, I was looking at you and him because he shook his head no too. So it just happens to be both of the same line. So it's just another way to write it. And you're going to see the IJK format quite often, actually. More often than you're going to see this format, because this format kind of looks like a point, which confuses people, and this doesn't. But you need to know both because they both show up. So let's, okay. I deleted a problem in between here. All right, so in this problem, they've given me two vectors. Is I, actually, you guys can read that. That's big enough that you should be able to read that. So we've got I plus 2j minus 3k and 4ai plus 7k. You'll notice that the I, j, and the k are bolded. Obviously, you can't write bolding. It's just to designate that as a constant, not necessarily a variable. Okay? There is a reason it's bolded. Sometimes when you're actually writing it, they'll use a fancier letter for it, so this way it's identified as something different than a variable. Because it's not a variable, it's a constant. It's an actual specific value in vectors. Like that, those ij's and k's are not going to change to something else. It's not like an xy. If I wanted to do 2a plus 3b, I'm going to do the exact same thing I just did before with the other points. Nothing really changes in that fact. So 2a is 2i plus 4j minus 6k. I just multiply it all by 2. 3b is 12i plus 21k. And if I wanted to do 2a plus 3b, I add them together. So I have 14i plus 4j plus 15k. And that's what it would be in terms of I, J, and K. All right, let's give you another one of those. Let's do one, a couple more of those before I go on. No. Let's do these two back. Before I go on to that. All right. So find me 4a plus 2b, and the magnitude of a minus b for those two problems.
Oh, is it? Okay.
That's all I missed. So the sum of them for the first one should have been 614. To do the magnitude, you actually have to subtract it first, then do your magnitude. You can't do the magnitude of each one and subtract them. It does not work. So if we were to subtract it, we get negative 12 and 5. So then if we're doing the magnitude of that, we have the square root of 12 squared plus 25, or 5 squared, which should equal 13. 144 plus 25, 169, yes. So my magnitude of that one's 13. We did 4 minus a negative 1. Those negatives always get you. All right. This one, even though it's written in a different format, is done the exact same way. So 4a is 20i plus 12j. 2b is negative 2i minus 4j. So 4a plus 2b is 18i plus 8j. Your magnitude, we have to subtract them first. So we've got 5 minus a negative 1, which is 6i, and 3 minus a negative 2, so it's 5i, or 5j. I. And then we find the magnitude of that. So it's the square root of 6 squared plus 5 squared. So 36 plus 25 is the square root of 61. So notice process doesn't change. It's just a different way to write it. It's like Celsius and Fahrenheit, 2 different ways to write the same thing. Yes. Nope, it's just the numbers. Because I and J, if you square it, it's still 1. Remember, I is just 1, 0, 0. It's just 1. So you're never squaring them or anything else like that. It's just another way to write the components. So. All right, one more thing we have to look for is what's known as our unit vector. The unit vector is a length whose, like, it's just like the unit circle, it's 1. All right, so a unit vector is a vector whose length is 1. I can change any vector into a unit vector. Okay, it's going to have the exact same direction. It's just the length is going to be just 1. So unit vectors are really good to tell me direction, but not really length. To do this, all we do is divide each part by its magnitude, because we in essence want to make it 1. So we're going to divide by how long it is. If we divide the length by how long it is, you get 1. So if we have our problem here, it's 2i minus j minus 2k. First thing I have to find is my magnitude for this one. So the magnitude of that is square root 2 squared plus negative 1 squared plus negative 2 squared. So we already did this, comes out to be 3. So now to find my unit vector, I'm going to take each of those and divide them by 3. So I have 2/3 I minus 1/3 j minus 2/3 k. And that's the unit vector. All right. Any questions with those? Okay. Now we ratchet it up 1,000%. Now we do applications. All right. So I have a 100-pound weight. It's hanging from 2 wires. I want to find the tensions in the wires and the magnitude of these tensions. Okay. So the first thing we have to do, we're talking about vectors. I need a vector. Okay. So let's draw a line here. Really? That's close enough. All right. So I've got a line there. If that's 50, what's that angle? Also 50, because alternate interior angles are the same. If that's 32, then this down here is also going to be 32 degrees, correct? Everybody agree with that? Okay. If I was going to make this a triangle, and 50 degrees is there. And I'm looking for basically that point right there. That's going to be my, so T1. It's not 500, that's 50. So your I, we have I plus J. My I, if I wanted to figure out the length of I, knowing this, which trig function am I going to use to find I? Cosine. So I have cosine of 50. Let's rewrite this. And as it sits right now, I don't know how long this is, right? So it's going to be the magnitude of T1. And which direction is this going? Is it going in the positive I or the negative I direction? This one's going in negative, so it's going to be negative that. Now, plus my up one, or my J, is going to be what? Same thing, so it's going to be sine. So it's the magnitude of T1 sine 50. J. So that is my vector for T1. Find me my vector for T2. All right, so it's T2. Yep. So that's T2. So those are my two tension vectors. Now, to solve this, we have to come up with what T1 and T2s are. We have to come up with, basically, we have to find those magnitudes at some point. Now we have to do a bunch of work. All right, so we've got these two. Those. And I need my picture still. So if I did T1 plus T2, so those are those two vectors, right? It's going to equal whatever this weight is as it's pulling down. So how much do we say this weight was? 100? And is it pulling up or pulling down? So it's minus 100. And since it's going in the down direction, it's 100. Okay. That's the vector for the weight. Let's switch it. Oh, this is a physics thing that I don't totally get. All right, so it's actually the negative weight because it's counterweighted. So it's going to be a positive 100J because the counterweight's pulling down, but the weight on the tensions is positive. It's a physics thing. Huh? Technically, it's what? Oh, statics, not physics. Okay. It's one of those classes that I, believe it or not, never had to take. All right. So we've now got, we're adding these two and setting it equal to 100J. What I want to do, so instead of, when we're adding them together, we want to add the I's together and the J's together. So I have T2 cosine 32 minus T1 cosine 50 I plus T1 sine 50 plus T2 sine 32 J equals 100 J. So far, so good? Okay, we're just taking basically the two pieces, we're adding the two vectors. So now I have two equations. Well, it looks like I have one, but I really have two. Because I can take this I equation and the J equation now and actually use them. So I have the magnitude of 2t cosine 32 minus the magnitude of t1 cosine 50 equals 0. Why is it equal 0? Because there's no I on the other side. So that has to equal 0. I then have, I'm going to switch this around just so those line up. It doesn't make a difference with the addition one, how to write it. And this one equals 100. All right, so I'm going to run out of room writing these all out. This is fine. What is it? How do I solve systems of equations? So we've got two variables in this case, got T2 and T1, those magnitudes. So as it stands right now, it's probably going to be a total pain in the butt to do elimination because I'd have to multiply it by sines and cosines. So probably not that way. So what's the other way we can solve it? Substitution. So I solve one of them for one of the variables and I plug into the other one, right? Let's solve the first one for T2 just because it's simple to do, and we'll plug that into the second one. Yes, I'm getting tired of writing. So if we solve the first one for T2, we'd move over the T1 cosine 50, and then we would divide it by cosine of 32. So T2 becomes that. And now that they both have T1 in it, I can pull out the T1. Okay. And this, I can do it. Calculate. Because there's no variables in there anymore. Yes, it's a bunch of trig functions, but there's no variables. So I can literally type that right into a calculator and get the answer. So sine 50. If you're doing it in your calculator, make sure your calculator is set to degrees. So sine 50 plus cosine 50 times sine 32 over cosine 32 in degrees. So plug that into Desmos. And I get that. So now what do I do to get the T1 by itself? I'm just dividing 100 by that. So T1 equals 85.64. Huh?
This part of it, the P1 plus the L1. So what didn't we have to find the difference for the 2 points?
No, it's a sum of the
Why
two.
is the J over there
This?
in between the P1 sine 50 and P2 sine 50?
This one? Because they're both positive. They're both going up. The signs are both going up.
I'm finding the difference of factors.
Nope, the sum of them equals the negative weight. So now that we got T1, I know that what we wrote originally was that T2 was the T1 cosine 50 over cosine 32. So we can plug the 85.64 into there and we get T2. So now we got the magnitude of T1 and the magnitude of T2. So we can take those. We had my original equations. Those were my original T1 and T2s. And we can plug in the T1 and the magnitudes. And we get our tension vectors. So the few pieces that you have to do when you're doing, that's why I said multiplying like the difficulty by like 1,000, because the rest of them were just simple problems, and now we're using applications of them, which is where we actually use the stuff. So we had to figure out the vectors based on the picture. So we had to take the picture and the information and come up with my two vectors for T1 and T2. And a lot of these are going to use degrees. They're going to use angles because you're moving things. Once you get your angles, though, it's pretty straightforward. It's typically going to be a cosine for your I and sine for your J's, because that's what your right triangles give. Then you use your counterweight, which in this case was 100, and then you basically are solving the equation for the missing variables. So after that part, the rest of the stuff is basic algebra. Well, algebra, not very simple algebra, but it's systems of equations. All right. So yes, it's a bunch of calculations, but it's steps more than difficult steps. And then the question wanted our tension vectors, so we plugged that back information back in to get the two tension vectors. Now, it would change, like the tension vectors would drastically change depending on the angle, those angles. So depending on where it's attached, those tension vectors would change. So if you're looking at the material used and how much tension it can take and stuff like that, that's where you're figuring out your attach points and stuff would be. All right. Let's see if I can do this in 2 slides. Nope, 1 slide. There's no way I'm doing it in 1 slide. That's fine. We just make another one. All right. Last problem. Train leaves Denver at 3 o'clock, going 400 miles an hour. Similar. So a woman's launching a boat from the south shore of a straight river that flows directly west at 4 miles per hour. She wants to land at a point directly across on the opposite shore. If the speed of the boat relative to the water is 8 miles per hour, in which direction should she steer the boat in order to arrive at the desired landing point? Okay. As crazy as it sounds, this is actually one thing that's, well, not necessarily with the boat, but a sniper has to actually pay attention to when they're shooting long distances. The wind will affect the bullet. So if you want to hit a target here, you might have to aim here so that the bullet would end up back to there. Same concept with this boat. So let's figure out our vectors to figure out the angle that she has to go. Okay. So what information do I have? Direction of the water. So it's going west. So the current vector, we'll call VC, is going to be what? negative 4i. Because we're going 4 to the west. And that would be in the negative direction. Okay, so if we're using here, that's my negative 4. That's my current vector. All right. So my boat is going 8 miles an hour, right? In some direction this way. So my vector for my boat is going to be 8 times what? It's the magnitude. So I'm going to multiply it by what? So if we eliminate the 8, what's my unit vector? Because basically it's a unit vector times the magnitude. Think back to my triangle. It's going to be I and j multiplied by my angle, right? Which I don't know. So it's going to be cosine theta I plus sine theta j. That I don't know. All right. So where does she want to? She wants to land somewhere up here, right? Due north, correct? Okay. So my J's so basically I want my J I don't know because I don't know how far across the ocean the water she needs to go, correct? But what do I know? What's the piece? I don't know my J. Do I know my I? What should the I be? At the end, when she lands, her I should be what? How far east or west did she go? She went 0. She didn't want to move, right? She wants to go due north, right across. So my I is going to be 0. So I have, if we take the two i's, so negative 4i plus the 8 cosine theta I, that has to equal 0. Since we're just looking at the I terms, I can in essence eliminate the i's because it's not a variable. So negative 4 plus 8 cosine theta has to equal 0. So how do I solve? Move the 4 over, divide by the 8. So cosine theta equals what? Well, if it moves the 4 over, I added it, so it's positive. So 1/2. So theta is going to equal what? What theta values? 60. 60 degrees. So she has to turn the boat so that this angle right here is 60 degrees. Has anybody ever been on a boat? Has anybody ever driven a boat? Do you know how you'd actually steer the boat? Which direction? Okay, so, but if I'm going north, so here's the problem. Well, kind of, yeah, because basically, she's not going this direction, right?
Yeah.
It's going this way. So she's not steering 60 degrees. She has to steer, it's north 30 degrees east is her bearing. So,
Go like all the way this way and then do it.
yeah, you know, you want to do more work there. So it's actually, the bearing is like that. So if you're looking north, you're going 30 degrees east of north. So as long as she's going 30 degrees east of north, the current is going to push her back. So she will land directly across at that point.
So if it's 45, you do this right north.
You can, because that is exactly northeast.
Yeah.
So yes. But bearings typically have the number between it. So, but yeah, 45 would be northeast, because if you're going past that, no, actually, because you can go all the way to 90. No, northeast, yeah, east would be 90. So yeah, northeast, and then you can go further that direction. So,
Your convention to always have a value be less than 45 degrees.
no, 90.
So this would be like east 60 degrees north, right?
No, it'd be north 60 degrees east. No, this is north 30 degrees east. If you're going 60, it'd be north 60 degrees east. If you're going 60 degrees towards
What
the
about
east,
east 60 degrees north.
that would be, yes, you could actually do it that way.
So is there a convention?
Yes, it's always north and south is first. Okay, now I understood what you were saying. Yes, you always want to do north or south first, because your compass shows north. So, all right. So there's just two examples on where you can use vectors. All right. No class on Thursday. On next Tuesday, we'll do the dot product. Next Thursday, we'll do the cross product, which are two ways to find angles. And then we're done. So your next